Hey guys, the objective of this video is to find the force per length from our pressure distribution, which we've developed in the previous two videos. So just a quick reminder of where we're at. What we've done is we've got our wall with the clay and sand layer, and we've developed pressure distributions for the clay and pressure distributions for the sand. So what we're going to do is we're going to combine this now. So we had a pressure distribution from the clay layer, which looked like this. So I'm just going to redraw this on this new page. So we had this depth was 1.41 meters. This depth was 4 meters. We had a stress of 13.8 kPa, and at the bottom here it was 32.3 kPa. Okay, so that was from our sand layer, and then in the previous video, that was from our clay layer. In the previous video, we found the pressure distribution for our sand layer. So I'm just going to add that below it because we had the clay layer and then the sand layer. So for the sand layer now, this will jut out further and it will become 46.2 kPa. So 32.3 is this length there, 46.2 is this longer length here, and we know that this depth was 2 meters. And this extended further out to 75.3 kPa. So all I've done is I've combined the clay layer and the sand layer, the pressure distribution we developed, and now we're going to be able to find the force per unit length. So just a quick reminder of what we're doing. We did this in the FlowNet video where we had a particular pressure distribution. So in our case it looks something like this. And we had a wall. So our wall is going, this is obviously our wall, the depth of our, total depth of our wall. So we had a 4 and 2 meter layers, which had a total depth of 6 meters for our wall. So we developed along our wall these pressure distributions in 3D. So it looks something like this. So this is into our wall. So I'm just going to draw it in red. So we know that the pressure distribution in our wall is an area load. So this, you can see that this is our area. It's the same shape, which is in kPa, and this is obviously in meters because that's the length of our wall. And we know kPa is the same as kilonewtons per meter squared. So all we're going to do is find the area of our shape. So I'm going to draw that in blue. So we're just going to find this area, and if we find that area, it's going to mean that we're going to get kilonewtons per meter squared multiplied by meters. That's going to cancel, and we're going to be left with kilonewtons per meter. So we're just going to have 1 meter on the bottom. So we get kilonewtons per meter, which is a line load which goes along our wall like this. So we're just converting pressure to a line load. If I were to redraw this a little bit nicer, we would have our wall, and we now, by multiplying these two things, by finding the area, have a line load on our wall. So all we have to do is find the area of this shape, and then that'll give us a line load acting along our wall. So we have two shapes in our diagram, our pressure distribution. We have a triangle. We have two triangles, and we know the area of a triangle is simply the base times the height on 2. And we also have a trapezium. So this is a trapezium, and the area of a trapezium is equal to the height on 2 outside of A plus B. Okay, so we have everything we need. The only value we need is this height here, because we're doing separate shapes. So we need to find that height, which will just be 4 minus 1.41, which is 2.59. So to get that, we just went 4 minus 1.41 will give us that length there, which is 2.59. Okay, so we're just going to go ahead and work out the total area of this now. So we know that the force is going to equal this area. So we've already established that before. So if we were to work this out, the area of our triangle here is equal to 1/2 outside of the base times the height. So the base is 13.8 multiplied by the height, which is 1.41, plus we have another triangle here. So that's going to be 1/2 the base times the height. The base is 32.3. So 32.3 times by the height, which is 2.59. And then finally, we have a trapezium, which is h on 2 outside of a plus b. So the height is 2 meters on 2 outside of a plus b, which are the two lengths. So 46.2 plus 75.3. So if we were to work these out separately, we would get 9.7 plus 17.4 plus 121.5, which will give us a final answer of 148.6 kilonewtons per meter. So there we've done it. We've converted our pressure distribution into a line load acting along the page. If we wanted to once again get a conceptual idea of what's going on, if I just get up the wall, so we now have along this wall, coming out of the page, we have a distribution of force, a line load of 148.6 kilonewtons per meter, which is acting like my pen. So it's coming in and out of the page. So it's acting like this along the page. Just one more time, we have our wall. We've converted our pressure distribution into a line load. So here's our wall, and we now know that the linear load acting on our wall is 148.6 kilonewtons per meter. Okay? Anyway guys, hope that helps.